Now let's come to 3 quite short subsections about wireless security and tools. So only one slide about TCP in wireless networks, because there's the course Mobile Communications also available, all the videos. Well, typically low transport layers should be independent of low layers. We saw how TCP is not independent of IP, but it should be independent of the link layers. But obviously TCP has been optimized for wired networks. So that was again this issue that TCP assumes packet loss is due to congestion in the network. In wireless networks, we have other reasons for packet loss, handoffs or handover. We have way burstier errors there. We have suddenly bigger delays with large variations in a delay. Just imagine you move from a wireless LAN into an LTE network or back. So the performance of the classical TCP in wireless network is rather poor. So all this cumulative echoing doesn't really work because we have burst errors. Cumulative echoing was nice if you drop a single segment, if you lose several. There are some approaches to solve the performance problem. Some of them break the end-to-end idea of TCP, split connection TCP, and some modify TCP, but then we have backward compatibility issues. Some tweak some of the parameters, like tweaking the initial window that in the end you burst into the wireless network and you hope that you're successful. And there are also newer transport protocols, different transport protocols. But you see, TCP has some issues there, but more, as I said, in mobile communication. Then what about security? There's special security for the network layer. There is no real security built into TCP. So when it comes to TCP and security, yes, TCP is vulnerable. And what is special about TCP? You can attack TCP. We can place encryption on top of it, but that's a different issue. Then we want to encrypt user data. But what about TCP itself? A very simple and old attack is called SYN flooding. You should be aware of this. So what does an attacker do? You start the 3-way handshake, but you stop after 2 handshakes. So how does it look like? The normal scenario, well known to all of you, is 3-way handshake. Perfect, fine. But what if you only have this 2 ways? 1, 2, and you don't do the 3rd step. Then it's a 2-way handshake, but the problem is this leaves kind of a half-open connection on the server side. So here, the server reserves at least, well, a port for this new connection that should come, but it never comes. And now, if you do this quite often, then the server reserves the ports already for this new connection, and after several, hundreds or thousands of half-open connections, the operating system simply has no additional resources. So this is a classical denial of service attack. So how you can kill a server within seconds, simply because the server waits. And for all these half-open connections, the server starts a timer and waits, and if there's no answer, it will sooner or later stop and, well, kick out this half-open connection, releases the resources. But if you have such timer, for example, set at 2 minutes, this takes a while. So that's a quite successful denial of service attack, but there are countermeasures. So against this DOS attack, and a countermeasure is, besides firewalls detecting this and kicking out the traffic, that's one solution, that also the devices, the hosts, can use so-called SYN cookies. The idea is we do not create a half-open connection. We simply don't do this. So all we do is we compute an initial sequence number y based on a hash function. And this is then our cookie. So this is the cookie. And when the client returns with an acknowledgement, the server recomputes the hash function and checks it. And if everything is fine, then you create the connection. This requires some computation, yes, this checking in the end, checking if this is okay. And so there's a compromise, if you have to be efficient, that you use this SYN cookies only if the table in the operating system with half-open connection grows beyond a certain threshold. So that's one of the ideas, that you do not let this table grow too much until you don't have new resources anymore. So this is a pointer, SYN flooding, SYN cookies. Check out literature if you're interested in more details. And how can you find out what's going on? Well, there are some simple tools for TCP. One tool, Netstat, a tool that helps displaying protocol statistics about, among others, TCP and IP addresses, routing tables, all these things. But, and that's the interesting part, you see the current state of the connections. We talked about the state machines, and here you can see the state. You can check the performance, the throughput in a network. You can generate TCP UDP streams, iPerf or TTCP, test TCP, similar. So it also helps you measuring throughput. And sure, you can use Wireshark. You just tell Wireshark, okay, grab a TCP connection. And here you see exactly our three-way handshake. 1, 2, 3. You see a SYN segment, SYN ACK and ACK. And you see exactly the game of sequence numbers. Be aware, these are relative sequence numbers. These are not the raw sequence numbers, but this helps you to follow the connection easier. That's the idea. So we have sequence number 0, which is raw, is just some way higher number. And we see this three-way handshake, acknowledgement, telling them the other side, this is the next I expect, and indeed, that's the next packet. So, and in this case, the fourth packet we grabbed in this example, well, this starts encryption TLS. So, if we look into such a packet with Wireshark, you find exactly all the components. We discussed ports. These are our ports used for multiplexing here. That's the port for multiplexing, the important part. Then, for example, we see this sequence number. So as I said, relative, and that's the real raw sequence number of such a packet. What else? Then we see raw acknowledgement number. This is when we start. There is no acknowledgement in the first packet. I mean, because the connection just starts. We also see that in this case, we don't have all the other flags set, only the SYN flag. Yes, because this is a SYN packet. So that's the idea here. So of the flags. We also see the window here in this example, urgent pointer, and also options like that we permit selective acknowledgement. Don't have to use go big N. So with Wireshark you can find out all these details, in this case of TCP. So some final questions to TCP. So why is TCP challenged in wireless and mobile networks? So what is really different? How can we attack TCP? What are countermeasures? And in literature you will find more ways of attacking these protocols. But please go ahead, play with the different tools, check out with Wireshark what you find in the packets. Maybe something surprising, you will find experimental content, non-standardized flags you don't find in the classical, in the RFC, like accurate ECN, something currently discussed, if this is something needed, what's the idea behind this. And what's quite important to see, although TCP started in 1974, the development is really far from being over. It's further improved for special applications. We don't know what the future will bring, that TCP will be one of the transport protocols, I bet still for the next 10, 20 years, but we don't know how fast alternative protocols will rise.